Thank you all for being here. I'd like to introduce you and welcome you to the master's thesis defense of Daniel Alvarez. Daniel joined our department in August 2024 to pursue a master's degree after receiving his bachelor's degree in applied physics at Loyola Marymount University in California. His undergrad research focused on fluid dynamics from a mechanical engineering lens, and he utilized experimental techniques like PIV, particle image velocimetry. So when I first met Daniel, I knew that I had to somehow try to convince him that he could be a great geoscientist. And I don't know what worked, but something worked because he agreed to come to Virginia Tech and to pursue research focused on river processes and Bedform. So Daniel has really had an incredible impact here at Virginia Tech in the 2 years he's been here. And really at the beginning, it's no small feat for somebody to pivot and build and go from the engineering background and fully integrate yourself into a geoscience department. And, I think that what we all know about Daniel is that from his background and perspective as a first-gen student, that he has a true knack for accomplishing really hard things. So it's not surprising that he did this really, really well. He jumped in head first. He taught 101 labs like earth science history, and he was teaching those labs as he was learning them. And he did so good. He had really great teaching scores, teaching assistantship reviews. He took courses in CEE and biological systems engineering in addition to our department. So he was truly like expanding his learning across all parts of the campus. And you can see that from this committee where we have Brian Romans in geoscience, we have Kyle Strom in civil and environmental engineering, and then we have John Schubel in biological systems. He presented his research at local, state, and international conferences, and he's done all of these things with tenacity and eagerness. And so I think that that's already a huge accomplishment, but he's also made amazing contributions to our department in service and outreach as well. To name a few, he supported GSRS as a volunteer and as an organizing member this year. And he led GCamp as an activity leader. And he was even highlighted with an awesome photo of him on the quad, like working with a student. And it was a photo in like the main center page of the College of Science Outreach magazine. So Daniel has always been engaged and ready to help and ready to jump in. And as a lab, we all know that we can really count on it. So after Virginia Tech, we are very proud to say that Daniel has accepted a position and he will be pursuing a PhD at Texas A&M University in the Department of Geography, working with Andrew Moody. Really exciting. Yay! And we're going to miss you, but we're so excited for your future. So Daniel, thank you for your the time that you've spent here at Virginia Tech and all the contributions that you've made. So with that, I'd like to introduce Daniel Alvarez. Take it away.
Thank you for the introduction. Before I begin, I just wanted to give a brief introduction about why we want to study rivers and their importance throughout history, both in past civilizations and current settings. Rivers have been a major center of civilization, specifically the first civilization known to man as Mesopotamia, where the civilization centered around the Tigris and Euphrates rivers for their agricultural benefits as they used the floodplain for farming. These have spanned across history from ancient Egypt, where the Nile River has been a major source of agriculture and transportation, and even in more modern settings where we see how the Missouri River has been a source of transportation for the Lewis and Clark expedition. We can see the importance of rivers and the need to understand how they evolved. Within our current settings, we use rivers for major sources of necessary resources like hydropower, transportation, and freshwater storage, where we can see how large hydropower plants like the Three Gorges dams actually generates power for surrounding civilizations and provides shipment routes for transportation of goods in the region. Specifically also, as I'm from California, I take a big liking to the Colorado River, and I think the Hoover Dam is like a major important part of the Colorado River and it supplies most of California with its drinking water. So it's been a major motivation of mine to understand how some of these rivers evolved since they supply so many things that we need in life. But as geologists, we know that we specifically care about rivers because of their geological implications in terms of sediment transport and erosion. They're major agents of erosion as they erode catchment areas based on high elevation slopes, which generate steep bed slopes and faster flow, and they can transport larger sediment sizes. And due to this high transportation energy, they erode catchment areas as they deposit sediment in what is known as a transport area in the larger river system. Within these regions, we see how sediments from upstream boundaries have been transported and deposited to their mild elevations and a reduction in bed slopes, which then decreases moderate flows as we pass through a continental scale. As sediment moves through the transport regions and flows move sediment, we see that basins with low elevations are majorly dominated by deposition and a low transportation energy, which then allows for river channels to be shaped through curvature by the flow specifically, where curvature can develop easier in lower elevations like transport and basin regions due to a smaller grain size and a more variable bed elevation. Specifically, we can see how curvature increases the shape of the channel, where we see low curvature channels can turn into river bends and then transform into oxbow lakes once these curvatures reach a maximum threshold as they migrate into their floodplain. However, today we're going to start by explaining how these processes occur within a channel reach beginning, just to talk about their hydrodynamics, to understand how these processes affect their morphodynamics over larger scales. Specifically within a low curvature channel, we can see that hydrodynamics are dominated by a gravitational force driven by elevation differences in the upstream and downstream locations of a river, where upstream locations, denoted by the right side of the channel, are driven and are accelerated in the downstream direction due to this gravitational force, where the gravitational force can be partitioned both into a vertical and downstream component, or what we're calling GX and GC. As the flow travels through the river, it speeds up due to this change in elevation. Though this image does not show a reduction due to frictional effects along the riverbed, flows do increase as they decrease in elevation, showing that increase in velocity, both in the downstream direction and as a function of elevation from the bed to the free water surface. But when we think about how this changes when we pass through a curved channel, there's actually an additional force incorporated into the flow dynamics. So to understand this, we see where flows coming in now from the left side of the screen into the right. We see that there's an increase in flow velocity due to this centripetal force in addition to this gravitational force, where flows that pass through a river bend experience like an additional force that you experience like when a car is making a turn. And as the car makes a turn, like the flow passes through the river bend, we see that the outside edges of that turn or the larger radiuses of curvature experience a higher acceleration due to that centripetal acceleration. This is both a function of that radius of curvature and the general flow velocity, where flows on the outer edge of curvature move faster and experience higher accelerations due to their higher velocities and larger radiuses. And then we see that flows on the inner edges of curvature experience slower accelerations as well. This is characteristic for most river bends, where we see that increasing radius or curvature will then cause higher accelerations as they exit the channel and the curvature itself. We can compare this to a real world application where we see that faster flows on the outer edge of curvature, denoted by the blue elevations or the blue colors on the river's image, deepen the channel through erosion because these faster flows have higher transportation energy. In addition, on their inner bank locations, denoted by the red or warm colors, we see that slower flows and deposition creates a shallowing of the channel, which translates into a lower elevation. This creates a variable bed elevation across the width of a channel, which shows how this velocity gradient shapes the riverbed itself. This also creates recirculatory currents in addition to its curvature. So as the flow passes through the riverbed, it adapts a helical recirculatory cell. Or if you think about it, it's just going to be an additional flow direction that forms in circular motion in addition to its downstream direction. As we see in cross-section 153, denoted by the yellow star on both sides of the screen, we see that outer banks experience higher flow velocities by the red coloring or the warm colors on the color map. And we see that their recirculatory strengths increase as well, denoted by the shape and lengths of the arrows as well. We can see that this increases in complexity due to the formation of two different recirculatory directions. And as we leave the river bend in cross-section 156, we see that these recirculatory currents decrease and that maximum velocity concentration shifts from the outer edge of curvature or the outer bank into the center of the channel again, showing how this transition from the curvature or the river bend hydraulics changes once you start to reduce that channel curvature and it responds like that low curvature channel. This leads to the larger development of river bends and general channel migration within the larger planetform evolution, where we can see these processes occur over a number of different steps. The first step to happen to transform a channel from a low curvature to a riverbed could be understood through a bank erosion, where flows will erode one side of the bank, and due to that erosion, they'll transport sediment across with the channel and deposit along their inner banks. This will create a variable bed elevation, and then as these processes reoccur over time, we can see that this outer bank erosion will then cause inner bank deposition, and these processes will then cause the channel to migrate laterally in the direction of its outer bank, while these recirculatory cells build this variable bed elevation. This causes the curvature to increase, where we can see in the GIF that these channels build their river bends and then form the oxbow lakes and cutoffs as they increase to a maximum curvature threshold. However, when we look at the larger planetform evolution, we know these processes take years or even longer to occur. So we want to understand how these processes occur over smaller timescales. And to do that, we're going to be looking at the riverbed morphodynamics. Specifically, we're going to be looking at bedforms, which are sediment structures. And today, we're going to be introducing a first type of bedform, which is a point bar. It's going to be a larger structure bedform where they build upon the inner bank deposition. And these bedforms migrate with the channel as they erode their outer banks and deposit along their inner banks, shown by the yellow square. However, these processes occur over longer times, and due to our analysis and our research question, we want to look at smaller time scales as well. So we're going to be looking specifically at dunes today, or smaller sediment structures along the riverbed. Dunes are classified by their triangular shapes, specifically their upstream and downstream facing slopes, where upstream facing slopes are classified as a spa side and downstream facing slopes are classified as a lee side. We can then calculate their geometric features, or what we're going to call their morphologies, based on their maximum and minimum elevations, what we call their crest and trough locations. Dune heights can be calculated from the distance of crest and trough locations, whereas their wavelengths or their general lengths between dunes can be calculated between successive trough locations. So a dune height will describe how tall it is versus the wavelengths will describe their spacings as well. And then today we're also going to talk about a mean lee side angle, which is going to be the magnitude of the downstream facing slope. However, there's one thing I'd like to point out that today when we talk about mean lee side angles, it's not going to be one single geometric characteristic. It's going to be an average sum of the downstream facing slope. Dunes form over a range of flow conditions as well, where we can see that under or above grain sizes of 0.2 millimeters, we see that dunes start to form based on their general flow velocities within the channel. Specifically, above 0.3 meters per second, dunes start to form, and then when we reach a maximum value of 1.2 meters per second, dunes transition from their primary state to either anti-dunes or upper plane bed. However, for most of today's talk, we will be sitting in a low or medium dune formation area, so that's going to be the major bed form that we're talking about today. Dunes are also the major agents of sediment transport along sedimented river bends, where there are sediment structures moving volumes of sediment over time. As they migrate, they erode their stop side and deposit on their lee side, showing how they maintain their triangular shapes in their downstream migration. The video also shows a time lapse of dune migrations within a flume, showing how these sediment structures transport volumes of sediment as well, where flow is denoted from right to left. Based on all of these factors, we want to understand how this hydraulic heterogeneity or these difference in flow characteristics within a riverbed alter dune shapes and sizes and their migration rate, or what we're going to call their morphologies and bedload fluxes. Specifically, we want to understand this because this is the smaller incremental steps of sediment transport that lead to a landform evolution, the larger landform evolution. So we want to understand how our spatial trends and our morphologies and migration rates compare to our understanding of riverbed migration, where we know that outer banks are eroded, inner banks are deposited, and this is how the channel migrates with floodplain. We're going to be looking at the sheet nose bend today for our study site, specifically because it is a river bend within the lower Missouri River. This study site is highly engineered, which I'd like to just note that there's hydraulic structures on both the inner and outer edges of curvature within this river bend. And though this alters the morphodynamics of our study site, this is an open source data set that was generated from a palette sturgeon habitability survey. So this provides an open source access of high resolution multi-beam echo sounder surveys for us to analyze bed morphologies over a 3-year period as well. Specifically, this allows us to analyze 21 surveys over a range of flow conditions and discharges, where we can see the discharges vary from about 7,000 cubic meters per second, allowing us to understand how dune morphologies and migration rates alter or vary across range of discharges, flow depths, and transportation energy specifically. To analyze dune morphologies, we're going to be using the Bedform analysis method for bathymetric information. And as a short explanation for this method, we split raster data or elevation data in XYZ format into 3 sections or 3 straight flow directions. And as we rotate these split sections, we can then calculate dune morphology based on the flow direction and how this denotes the stoss and lee side of the dune. We can then use the geometric characteristics described earlier in the talk to then calculate dune heights with lee side angles. Alternatively, we can use the Gunneralp and Rhodes method described in the 2008 paper to generate the river center line from bank points on each side of the bank or on each side of the channel. And then we can use the river center line to build a curvilinear grid to interpolate elevation points into curvilinear coordinates, thus creating a consistent flow direction for the bathymetric data. This allows us to calculate the morphologies in one single run, since now the flow direction is constant along the streamline axis. We can then use the curvilinear grids used for interpolation to return points back to Cartesian coordinates, where we then analyze how dunes vary within a single bathymetric survey based on their X and Y locations, where Bambi exports a text file containing these locations and information on their heights, mean wavelengths, lee side angles, and their flow depths. We're also going to be grouping these points or dune morphologies in terms of their spatial locations within the channel, specifically using 20 polygons within the sheet nose bend. And to do this, we're going to be talking about their lateral and longitudinal variability. So whenever I say a longitudinal variability, I'm going to be talking about their streamline groupings, which combines polygons within one given width of the channel and analyzes how these dunes vary as you go through the river. Specifically for their longitudinal variability. For their lateral variability, we're going to be talking about their cross-section grouping, where we're going to look at how dunes vary in terms of a distance from their outer to inner banks. We also exclude the first set of polygons within our cross-sectional grouping, just to note that there is an inflection point which swaps the location of outer to inner banks between our study. In addition to our spatial analysis, we'd like to incorporate force balancings into our dune scaling relationships to understand how sediment transport processes alter these morphologies and provide a more accurate prediction for our morphologic variability. To do this, we're going to be looking at specifically the bed shear stress, which is a force per unit area acting on a single particle. You can also think of this as the weight of the water column displacing a single particle. We can then create a ratio or define a ratio called the shield stress, which is going to be the bed shear stress divided by the weight of the particle inside the water column, or the relative submerged particle weight. Then using a resistance to movement threshold called the critical shield stress, we can then create another ratio to describe the particle's movement as a function of its displacing and resistive forces. To calculate this, we will need the energy slope, also known as the water surface slope, and we get these values by interpolating the water surface elevation along the river center line from both Waverly and Napoleon, Missouri. So to do this, we use Napoleon, Missouri's USGS gauge data to denote an upstream water surface elevation, and we can denote a downstream water surface elevation using Waverly, Missouri data, and then interpolate water surface elevations across the river center line. We can then crop the data to our study site and calculate the slope based on the slope of this water surface elevation line, shown by figure C. And lastly, to calculate bedload fluxes, we're going to be using two successive bathymetric surveys to calculate a difference between dune morphologies. And then from this, we can then calculate a flux quantity. But to do this, it's going to take a little bit of explaining. So we can calculate dune migration rates based off of successive surveys, where dunes are assumed to be purely translational, or they don't change shape as they migrate in the downstream direction. When we see this, we can see that each line denotes a successive survey, and that the dune leaves a footprint within their lee side as a lee side deposition footprint. We can then see how a transport rate is calculated from this lee side deposition, assuming that they're purely translational, by getting an area flux of sediment and then dividing it by the amount of time that's passed between successive surveys. Assuming that dunes only erode on their staw side and deposit on their lee sides, we can then calculate a sum of area deposition for each channel region, or what we're going to be using as our polygons today, to then get a displacement of the dunes based on their lee side deposition. To do this, we need to know how many dunes are in each polygon, and we also need to know how long or the width of each polygon is based on the nitrar at all methods. We can then transform this displacement into a flux by calculating the net change in elevation per polygon. So multiplying this displacement by the change in elevation will give us an area, and then we can calculate flux by dividing that back by the time between survey. To then answer the research question, we want to analyze how dunes vary across all surveys. Specifically, how do they vary across discharges and thus flow depths? And do these flow depths and discharge relationships accurately describe their morphological variability? We first look at dune heights, where each point describes average values for a successive survey. And we see that dune heights do scale with flow depths, or sorry, discharges. As discharge increases, dune heights grow bigger on average, and they become more variable, denoted by their standard deviation. We can also compare this to their flow depths, where dune heights also increase as a function of flow depth. They become more variable, and we can compare them to their characteristic scaling relationships, where dunes are assumed to be 1/6 of the flow depth, as described by Yall in 1964. However, this does show high error when considering our real data results from the field, constituting about 170% of error between our predicted result and our measured results from the snowspan. We can do a similar process for wavelength, where we compare wavelengths for each survey across discharges, and wavelengths do increase as a function of discharge as well. However, their variabilities or their standard deviations aren't as much of a function of discharge, showing that these scaling relationships don't uphold as much for wavelengths specifically. Similarly, we can use flow depths to show that they do increase as the water surface elevations increase. However, their standard deviations aren't a function of flow depth, and their scaling relationships, where they're assumed to be 5 times the flow depth, show even higher errors of 200% as well, as according to y'all in 64. In terms of doing least side angles or mean least side angles, like we were talking about earlier, they aren't a scaled function of discharge, and they center values around 10 to 12 degrees. Specifically, their standard deviations are about half their magnitude of average values, showing that there's a more consistent control on least side angles across all of discharges. And then we can split our least side angles into different classifications based on the classifications by Lefebvre and Cisneros 2023 to understand how these populations change despite a pretty constant least side value across all discharges. We see that low and intermediate least side angles, or 10-degree and 10 to 17-degree least side angles, decrease as a function of discharge, while their high least side angle counterparts increase as a function of discharge, showing that though these populations increase and decrease, they swap almost, keeping this average least side angle the same for all discharge or for all discharges across the surface. Thus, we show that dunes can be described as a function of discharge and flow depths. However, high percent errors within both of these measurements do lead us to believe that there's better ways to describe these morphologic variabilities. So what we're going to go into now is the spatial variability of both of the dune morphologies in terms of their longitudinal and lateral direction, or how they vary across the lengths and widths of the channel. And then we're going to see if these values change as a function of discharge as well, to then analyze how transportation affects their value. Specifically for dune heights, we can split heights in terms of their outer bank locations, outer center locations, inner bank locations, and inner center locations. Where the graphs here show warm colors as higher discharges and lower cooler colors as lower discharges. We see that dune heights do increase on the outer banks of curvature and decrease as you start to go toward the inner bank for all discharges. When we look at different discharge quantile trend lines, or the lowest 25th quantile discharge and the highest 75th quantile discharge, we see that dune heights consistently decrease from outer to inner bank, showing general trends regardless of their discharge magnitude. Similarly, for streamwise belts or their longitudinal variabilities, we can see that dunes decrease as they pass through the river bend and pass through the apex of the river bend. However, due to a low curvature channel, we see that these values show lower magnitude of change across longitudinal variability. In terms of their wavelengths, we can do the same process by describing their lateral and longitudinal variabilities, where all discharges denote little to no change within their lateral variabilities. However, when we split their discharge magnitude, we can see that high discharges have higher outer bank wavelengths and lower inner bank wavelengths, and this relationship switches for lower discharges, where outer banks actually have lower wavelengths than their inner bank counterparts. This kind of contradicts what we usually expect from the Yallen scaling relationships, where now lower discharges are actually creating longer dunes. That's surprising. In terms of their longitudinal variabilities as well, we can see that upon higher discharges, dunes become small, or dune spacings become smaller as they pass through the riverbed, and upon lower discharges, they become bigger when they pass through the riverbed, noted by the red and blue line. So yet again, because of a low curvature channel, these variabilities do not compare in magnitude to their lateral variabilities. In terms of their least side angles, we do see consistent variability throughout all discharges in terms of a width of a channel, where outer banks have steeper downstream facing slopes, while inner banks have like smaller least side angles, so to speak. But then when we look at their discharge relationships, we can see that as discharges increase, least side angles become more uniform across the channel. And across lower discharges, we can see that this variability increases, where outer banks of curvature actually have higher least side angles than lower banks of curvature have, inner banks of curvature have lower least side angles. Longitudinal variability shows similar trends where these side angles decrease as they pass through the apex of the bend. However, these values are fairly consistent, ranging around 10 to 12 degrees. So now that we've shown that dunes vary in terms of their lateral and longitudinal variabilities, and it's as a function of discharge as well, we want to incorporate our force balancing that we described earlier in order to accurately predict how these morphologies vary for a range of fluid conditions. To do that, we're going to be comparing the heights by a function of flow depth and transport stage, or that ratio of displacing and resistive forces like we described earlier. Relative heights describe dune heights as a normalized value to the flow depth, and then we're going to plot that by transport stage to show how these values change as sediment transport values increase. Upon lower discharge or upon lower transport stages, we see that dune heights are larger in relationship to their flow depths. And as the transport stage increases, we see that these values decrease, showing that even though these flow depths are increasing, the dune heights are still not increasing like we usually think. This also shows that as transport stages increase, that the dunes experience more erosion specifically. Within the polygons, you can also see that colors denote the spatial locations by the graph on the right, where circles denote the furthest upstream values and then pluses denote the furthest downstream values. And we can also see that inner banks and outer banks of curvature have the lowest heights, and then centers of the channel have higher heights as well, specifically within transport state relationships. We also can compare these to experimental data relationships where Bradley and Vendetti in 2019 shows that these relationships are quadratic functions. However, when we compare this with real field data, we can see that these quadratic functions change shape, where they show net decreasing values instead of a characteristic maximum threshold, increasing and decreasing values, denoted by the red line, which denotes the maximum increasing threshold from experimental data. This is likely due to higher transport stage magnitudes seen within natural rivers rather than experimental flume. When we look at their spacings or their wavelengths, we can normalize these values by flow depths as well and analyze how they vary over transport stages to predict further how dunes will evolve over different sediment transport processes. Specifically within relative wavelengths, we see that the lowest wavelengths occur within the outer and inner edges of curvature, and that these values constitute higher transport stages with experimental data as well. We also see a similar decreasing quadratic function with no increasing threshold as well when compared to their experimental counterparts. So this shows that as discharges or transport stages increase, we see that dunes get smaller and their spacings get larger in terms of their flow depths, showing how they get further eroded as these transportation energies increase, whereas their interbank counterparts don't experience similar phenomena. In terms of their least side angles, we actually do see a characteristic threshold of increasing and decreasing values, where least side angles start at about 10 degrees and hit a maximum increasing threshold and then start to decrease as well, which is a similar shape seen to experimental trials analyzed by Cisneros and Best 2024. We also see that least side angles are smallest in the inner banks of curvature yet again, and largest in the center of the channel as well. And as these transport stages increase, we see that least side angles start to go back to their low angle classifications, likely due to a high sediment transport on the side. So to analyze how all of these values evolve over discharges, we split discharges yet again by their total, their 25th, and their 75th quantiles to then produce statistical tests to analyze if their means differ and their regression results or their correlation results between different predictive variables and their dune morphology. But for today, I'm just going to be showing you both correlation matrices and linear regression. So for the correlation matrices, plots on the right will be showing, or plots on the left will be showing you all discharge values, where we can see how heights vary as a function, or how heights are correlated with discharge, transport stage, lateral slopes, and curvature. And then plots on the right will show you the top 75th percentile discharges as well. Within these correlation results, we can see that discharge and transport stage are the highest correlated variables for dune heights. However, as we reach higher flow velocities and discharge rates, we can see that lateral slope gains an increasing importance in terms of their correlation coefficient. Similarly, for wavelengths, we can see the same trend where discharges and transport stage predict all flow strengths or all discharges at a higher rate. But when we split them into their extreme values or their top 75th percentile, we can see the increase of lateral slope coefficient, showing the need to incorporate this complexity of channel slopes into our predictive measure. In terms of least side angles, discharges actually aren't great scaling prediction for least side angle magnitudes. However, transport stage and lateral slopes still show the highest correlation coefficients for all discharges. And when we look at the high value of discharges as well, we see that channel curvature starts to have a noticeable impact on the correlation coefficient. So to test this, I'm just going to be showing you linear regression results between heights and lateral slopes versus heights and transport stages. And just for the sake of time, I'm just going to be showing you heights, but I'd like to note that heights and lateral slopes upon higher discharges actually show higher correlation coefficients compared to their transport stages, showing how transport stages don't accurately predict sediment transport processes, particularly for dune morphologies on high quantities of discharge. And it also highlights the need to incorporate these further complexities within our scaling relationships. So this leads us to answer the question of how does this vary for bedload fluxes? And does this value, or do our flux values vary as a function of discharge, lateral slope, and curvature? We see that lateral slope and curvature have an impact on our morphology. Specifically for bedload fluxes, we don't see a lot of change within our methods to calculate, or we don't see a lot of transport within our low discharge measurements, denoted by the red line. However, when we see our higher discharges or our top 75th percentile discharges, denoted by the blue line, we can see a high gradient of lateral bedload fluxes within our widths of the channel, where outer banks of curvature experience higher erosion and inner banks of curvature experience less erosion. This is in context or in agreement with what we know about how river beds migrate, where outer banks are eroded and inner banks are deposited, and this is how the channel migrates. Specifically within their longitudinal variabilities as well, we can see a similar trend of low discharges having close to zero flux quantity, whereas higher discharges show higher erosion within the apex and lower downstream areas of the riverbed. We can connect these values to dune morphologies to see which ones predict how much sediment is going to be translated in terms of translational fluxes. And to show results in a timely fashion, I'm just going to be talking about the highest discharges or the top 75 percentile discharges denoted by the blue line, where we can see that mean heights and mean wavelengths have the highest impact on translational fluxes. And when we think about this, we know that mean heights, as they increase, the dune becomes taller. And as the wavelengths increase, they become longer, thus showing how the area of sediment that the dune encompasses increases both the height and wavelength. Whereas least side angles don't really control as much of the amount of sediment that the dune is transported. Though least side angles can be attributed to other types of transport other than this translational flux. We can then compare our bedload fluxes to curvature and lateral slopes again, curvature and transport stage, to then see if these relationships are better predictors for bedload flux as well. However, due to a low curvature channel, we don't really see statistical values or significant values for curvature and transport stages can be seen as a more dominant predictor for flux values across low discharges. Across high discharges, we do see a difference in lateral slopes, where we see that the correlation coefficients for both lateral slopes and bedload fluxes increases at higher magnitudes when compared to their transport stage counterpart. Further exemplifying that we need to incorporate lateral slopes into our transport calculations in order to accurately predict these extreme events. So just to wrap up everything that we've shown you today, we've shown you that heights and wavelengths scale as a function with discharge and flow depth, though there's high error in our scaling relationships, specifically when talking about reach average dune morphology. Their lee side angles are dominantly 11 to 12 degrees, and these high angle populations increase when we're talking about reach average values. However, these reach average values oversimplify the spatial complexities of dune morphology and their variabilities, where we see that heights actually increase as a function of outer and inner banks, or as a function of flow depth within the list of a channel. And that's not exemplified by their reach average value. Wavelengths also show characteristic values where we see that they increase from outer to inner banks upon high discharges and decrease from outer to inner banks upon low discharge. Though this is different from what we'd expect, I'd like to note that low discharge trends are likely due to hydraulic structure alteration of the channel, where these hydraulic structures limit the amount of sediment being supplied to inner banks of curvature. So these dunes are responding in a different way because of this alteration, thus altering why we see, altering why we see a difference in dune wavelengths in terms of low flow depths. In their lee side angles, we do see a high variability in lower discharges, and as these flow depths increase, we start to see the channel reduce that variability. So we see that spatial results exhibit higher variabilities when compared to the reach averages, thus showing the need to incorporate these spatial variabilities within our hydraulic roughness quantities and transport calculations, and that reach average results oversimplify these variabilities across discharge magnitudes. But how does this translate for transport stage quantification? We maintain our spatial variability by using polygon averages with transport stage, and we incorporate flow depth relationships by normalizing by the height of the wavelength. So we kind of combine both methods with our transport stage relationships here. And they exhibit similar quadratic relations as predicted to experimental data, showing that same quadratic fit, except as a different decreasing value as well. So these relationships do uphold for field data. However, when we reach extreme values of discharge, like their very high and very low discharges, we see that their correlations decrease. So we ask the question of why these values decrease, specifically their heights, their wavelengths as well. When we look at higher transport stages or higher discharges, so to speak, we know that flow velocities can increase within a channel. Thus, we can be pushing R down on the dune formation chart from the dune range to the upper plane bed, which has been shown by previous publications and experimental results, showing that dunes bedforms transition from dunes to upper plane bed upon higher transport stages as well. This can be likely due to an increased transport through the water column versus the riverbed specifically. In addition, these higher flows within riverbends have higher complexities, where we know that riverbends experience super elevation or a difference in water elevations across the width of the channel, where this now edits the energy slope that we were using to calculate the shear stress. And we see that there's going to be a higher transport stage or bed shear stress on the outer edges of curvature and a lower bed shear stress on the inner. This also affects their recirculation and intensifies the secondary flows, which can increase the lateral transportation of sediment due to these recirculatory cells. So as flow depths or discharges increase, we can see that these hydrodynamics become even more variable than what we first described, thereby altering their transport stage relationships and showing the need to incorporate these within a transport calculation. And to summarize our results in terms of a general trend or interpretable figure, we can show how lateral slopes and discharges alter morphologic variability by the following steps. An increase in discharge will increase flow depths and generally the size of dunes in the channel. And as we increase this lateral slope, we can see a variable flow depth develop across the width of the channel. This will make dunes in the outer bank bigger than dunes in the inner bank and increase the erosion on the outer banks of curvature, thus leading to a stronger impact of the lateral slope and a high spatial variability across the single width. Within high discharges and high lateral slopes, as we decrease flow depths, we see the size of dunes decrease as well. And when we decrease the lateral slopes, we can see that the flow becomes more uniform across the width of the channel. Thus, the dunes in the outer bank will become similar sizes to their inner bank counterparts, and we can see that this translates to a low erosion within our results specifically. This also can translate to a low lateral slope impact, thus causing a low spatial variability within the channel in terms of dune morphology and fluxes. So just to summarize, we know that spatial variability is quantifiable due to our results and is oversimplified by reach average quantities. We know that transport stages accurately show dune morphologies within field data. However, they oversimplify morphodynamic processes at higher transport stages or higher discharges, thus showing the need to incorporate lateral slopes and their impact on morphologies and migration rates during these higher values. We would also like to thank the USGS for the data publication, as well as the Columbia Environmental Research Center and Carrie Elliott for publishing the data as an open access source. And I'd also like to thank Dr. Julia Cisneros and the Department of Geosciences for funding this research as well, and giving me the opportunity to present my work. Thank you.
Okay, thanks, Daniel. That was a whirlwind. So much fun there. We are happy to answer some questions. We have about 12 minutes for questions. If anybody has any, or anybody in the Zoom, if you want to unmute yourself, we'll be able to hear you.
This is Carrie. Can you hear me?
Carrie.
Yeah. So I had a question on the sediment transport calculations, because the surveys were approximately 1 week apart, right?
Yes.
So I think you might want to look at, so at higher flows, those dunes are moving about 3 meters an hour. I've done a bunch of repeat, like same day measurements. So I wonder, I mean, it seems like they would be like 500 meters downstream if it was a weekly space.
Yeah, I think we ran into that issue too when we were trying to calculate deformation fluxes as well. It was kind of hard to correlate both of the profiles as well. So these flux values are more representative of net transport. So they could be estimating the amount of sediment being transported. This also can explain lower depositional areas as well. But we still see kind of like a deviation from a steady state result where these like week-long results, or these week-long transport results still show a slight increase in the outer banks of curvature. So I think even though it is kind of far spaced in time, it still holds some validity in the results, though it's not a high magnitude of transport.
You might want to word it more geomorphic change, because the dune tracking, it's just, I think within a week, it's just, the dunes are so far, just because the daily, I mean, I'm seeing 3 meters an hour of movement. So you would want to have measurements that were a lot closer than the weekly. So it might be the wording of how you describe the change. But great work. This is really cool.
Yeah, I agree. But thank you.
So I'm wondering what type of sediment was present in this river? Was it sandier, was it muddier? And then depending on what that is, would you expect to see similar results or like this trend continued if it was like a different type of.
Yeah, so I kind of oversimplified a lot of the sediment transport properties and then showed with the equations as well. But we don't really classify, so you can classify by sand and silt, but what we use is a characteristic value for the sediment size called a P50, where it's basically like a mean particle size. And we assume a mean particle size of 55 millimeters, or sorry, 0.55 millimeters. And this is a value used by different hydraulic simulations for the lower Missouri River and has been confirmed by AECP measurements as well for different sections of the lower Missouri River. So it does constitute a bit of higher error within the sediment transport calculation. However, it's just what we have to work with. There's not sediment data from this specific survey.
Yeah, this is great. I just have a question. You talked about that really high uncertainty, and I'm curious on, do you think that's just kind of like just in general, it's always going to be that high, or do you think that maybe because you kind of talk about how this stream being like altered kind of made you some of the things you'd expect didn't behave as they expected? Do you think that drives that uncertainty? And do you think there's a way to like account, being that a lot of streams now are being like altered for those more general? I'm assuming they're more general probably because it's easier and faster to do, but I don't know, I'm just like curious, do you think like there's like if it's altered, you can expect that to be greater, like a way to factor that in so those would go down? Or do you just think it's just, I guess, innately high uncertainty?
I do know that wing dikes do alter the like sediment size within the interbank region, specifically downstream of the structures. However, I think there's also just a pretty higher uncertainty in terms of transport calculations at times due to the impact of a sediment size. Specifically, like if we're assuming a sediment size as well, there's always going to be a general uncertainty. But I don't have these in these slides, I have them in the discussion slides, but I can say that grain sizes, assuming that if it doubles in size, can constitute roughly like almost 85% error. So it's basically an order of magnitude.
Amazing presentation. I was wondering at the very beginning when you talked about the types of data that you have, you showed like kind of a general graph of, I think it was flow over time.
Yeah.
It looked like it was decreasing from when your data collection started through to today. And I was just wondering if you have any idea why that is.
I think I noticed that it's the hydro graph,
Yeah.
and some of them do seem like order of magnitude higher. I
Yeah.
agree. The top one actually does constitute like a 1% daily load cadence from Waverly, Missouri. You can probably link this to potentially like a dam output, but I'm not sure why this is such a high magnitude. It just provides a really nice range of flow depths and discharges for us to analyze the morphology.
This is Carrie again. Do you see any signs of sediment hysteresis, like sediment sort of changing over the course of the flood events?
Like bedform hysteresis, or
Yeah, bedform hysteresis.
yes, I would always feel like there would be, especially at some high discharges like this. I don't think we got far enough within the time to really answer that question to a full extent. And that would have been a very interesting topic for a PhD as well, where trying to make that one of the chapters. But I don't know if I can answer that question to a full extent given the work that I've done.
Cool. Yeah, I think that there's some sediment transport variability. This flood in 19 was really, really big. And I think that some of the changes in dunes could be explained by like sediment being blown through the system over the course of that big flood. But that's kind of a hypothesis I've seen in these different floods on the Missouri.
Interesting also, I think it was actually just yesterday. I think there was like one dune that was like splitting as well in the 2020 flood, but I wouldn't know if it's considered hysteresis at that point.
Great, thanks.
Thank you, David.
All right. Okay, well, thank you all for being here. Thank you, Daniel. It was a great talk. Yeah, we can send you off and we're gonna kind of pack up and head over to the private exam, but you get time to talk to them first. Thank you all. Thank you all for joining. Thank you so much.
Or 4052, but it also is.
Stop the recording.